lecture about hybridization involved 3 different molecules, ethane, ethene, and ethine. I'm going to draw those now. Organic chemistry, the ANE ending is associated with single bonds in the molecule. The ENE ending is associated with having a double bond somewhere in the molecule. And the YNE ending is associated with having a triple bond somewhere in the molecule. You'll also notice these all begin with the prefix BTH, which indicates 2 carbons. So next we're going to talk first about a little bit on orbital overlap. And there are 2 major types of bonds that we're going to be talking about today. The first one involves end-to-end overlap of 2 s orbitals. When 2 s or spherically shaped orbitals overlap each other, they form what we call a sigma bond. It's the result of 2 orbitals with end-to-end overlap. This can also occur between an s orbital and a p orbital. P orbitals have more of a dumbbell shape, and when the end of a p orbital overlaps with the end of an s orbital, you also have the formation of a sigma bond. This can also occur between 2 p orbitals as well. And there are 2 p orbitals with end-to-end overlap, and these also have a sigma bond. Now, there's another type of bond called a pi bond, but it involves the overlap of 2 p orbitals when they're side by side. That represents one bond. That's called a pi bond, when 2 p orbitals have side-by-side overlap. So now we're going to tell the tale of hybridization. And in the beginning, we've taught you about the electron configuration for carbon. We're going to focus on the 3 molecules, ethane, ethene, and ethine. So I'm going to start drawing that, and then I'll come back and talk. that the electron configuration for carbon is 1s2, 2s2, 2p2. That's still the same. And we taught you that an orbital fill diagram for that element would appear as I have drawn. However, if you look at the tetrahedral shape of the carbon molecule, if you can remember building it, we had the black atom in the middle, and then we had sticks coming out, and they were at 109.5-degree bond angles. That was the most that four things around the central atom could space themselves from each other, and 109.5 was the optimum bond angle. Because remember, electrons repel each other. Well, really, when you think about it, these orbital diagrams don't really reflect what's going on in a tetrahedral molecule. A tetrahedral molecule has four very symmetrical bonds. These electrons in these orbitals don't really represent that. So we're going to show the formation of four new hybrid orbitals. We're going to take the s orbital, each p orbital, and we're going to blend them together. And we're going to make four new orbitals that are of equal energy level. Equal energy level also means that they are degenerate orbitals, all on the same energy level. I'm going to place my four electrons in each of one of my brand new hybridized Sp2 hybrid orbitals. Now when you take a look at that, that makes sense with the tetrahedral nature of the carbon atom. You have four equal electrons with minimal electron repulsion. That represents the actual drawing or structure, not the drawing, but the structure much better than the original orbital fill diagrams that we started with. So each carbon really has that configuration. Now, I'm going to draw this out and show the formation of the sigma bonds around the carbon atoms. The new bond is a hybrid bond formed between the s and the p orbitals. It's probably got a spherical shape, a little dumbbell shape. I'm just going to make mine look oval. Okay, so when each carbon in ethane contributes its very first hybrid electron, it will form a sigma bond in the middle of the molecule. Now I'm going to take the other sp3 hybrid electrons and place them around each carbon. We still have 6 hydrogens to place in this molecule. So those electrons are a region of electron density that we just drew. So a positive hydrogen ion would find those very attractive. And so the hydrogens are going to bond to those areas of electron density. Each of those bonds is also a sigma bond because it is the result of end-to-end overlap. There are 7 sigma bonds in this molecule. hybridization is called Sp2 hybridization, and it is characteristic of all tetrahedral domain molecules. Alright, so that tells the tale of methane. Now we're going to move to methane, which we already know has a double bond. So we're going to create the same diagram, only we're going to show how it's slightly different. This time, instead of hybridizing all of the orbitals, we are only going to take 2 of the p orbitals, and we're going to take the 1s orbital, and we're going to form 3 new hybrid orbitals called Sp2 hybrid orbitals. We're going to leave one of the p level orbitals alone. Now I will place an electron in each of my new hybridized orbitals, and I will also place the remaining electron in the higher energy p orbital. Now I will draw this one and show you how the overlap works in Sp2 hybridization. The first bond in the double bond is a sigma bond, but it's the result of end-to-end overlap of 2 of the Sp2 hybrid electrons, orbitals, in the center of the molecule. There are 2 more hybridized electrons for each carbon, which I'm now going to place around the carbons. Since there are 4 hydrogens that need to be placed around this molecule, they will find those regions of electron density attractive, so the hydrogens will be placed next. So far in this molecule, I have the formation of 5 sigma bonds. Alright, so now I've placed everything except for that higher energy p electron. We know that a double bond has more energy in it than a single bond. This is due to the fact that that p electron has a higher energy than its hybridized electrons. So this is going to result in a pi bond, which will have orbital overlap. those orbitals really represent one bond, and the p orbitals are enveloping really that entire carbon area. That's where those two electrons have the highest probability of being found. Whenever you have Sp2 hybridization, it's associated with trigonal planar molecules. In this particular molecule, there are 5 sigma bonds and 1 pi bond. Now we're going to take a look at the last example, which is ethine. In this type of hybridization that we see in ethine, we are going to blend one s and one p orbital together to form 2 new hybrid orbitals called sp hybrid orbitals. We will be leaving 2 of the p orbitals alone. I will redistribute the s electrons, the original s electrons, to go into each of them as a brand new sp hybridized orbital. Now I have 2 electrons in each carbon that are at a higher energy level than their 2 hybridized companions. We know that triple bonds contain more energy than double bonds. This is the reason why. Once again, the first bond in this molecule is a sigma bond. We're going to take the sp hybridized electron, 1 from each carbon, and form the sigma bond in the middle of the 2 carbons. That leaves 1 sp hybridized electron left. We'll place it to the side. Once again, the hydrogens will attach here. So now I am left with 2 higher energy p electrons. They are both going to form pi bonds around these central atoms. The diagram will be a bit messy. The second bond forms a pi bond. The second bond is a pi bond formed from one of the higher energy p electrons from each carbon. And the third bond is another pi bond formed from the other p electron. different orientations in space, which is very difficult to show on a flat surface. Anything with sp hybridization will explain linear domains. Now, so far we have not disobeyed the octet rule, but there is a lot of controversy right now about orbitals and the d orbitals having hybridization. I will show you what the older textbooks will have in it. However, newer textbooks are not going to talk so much about dehybridization because scientists aren't exactly sure if it really occurs or not. But the old school said that trigonal bipyramidal domained molecules would exhibit sp3d behavior. So on top of an sp3 hybrid system, you would overlap the first of the d shapes. Again, for octahedral, you have 6 domains around a central atom. So that would be an sp3 system with 2 d shapes overlapped around that. These 2 shapes are in dispute right now. They've sort of been debunked by the scientific community. So on the AP test, you won't see these 2, but you will see sp, sp2, and sp3.